Let us discuss the concept of electric field with the particular application to a point charge for now. We saw that if we have a charge uppercase Q and a charge lowercase q situated at a distance r between them, there will be a force of attraction or repulsion between them given by Coulomb's law. Let's focus on charge little q. So we see charge little q with a force, let's say a force of attraction towards charge q. So the question is, what causes this force? And for this, we have to, perhaps it is a good idea to go back to the gravitational field. We had the Earth of mass m, and we have an object of mass little m. We know that there is a force of attraction between the two objects. If I'm concentrating on object little m, I have the force being equal to m multiplied by acceleration of gravity g. But where is g coming from? G is coming from the big M object. And we saw in the video on gravity that actually this g, it is an acceleration, but more importantly for this problem is a strength of the gravitational field. It is the intensity of the gravitational field, and it should be labeled as gamma. But because gamma turns out to have units of acceleration, we call it acceleration of gravity, and we are using it in all our kinematics and dynamics problem in the early stages of this course. But the important thing here is, again, that there is a field produced by the Earth, say, and this field acts with a force on an object that I bring there, and I'm calling this object probe mass. Something similar will happen here. I can call this charge probe charge, and I'm bringing this charge in the vicinity of the uppercase Q charge, and the field produced by this charge will act with a force upon this charge. Now, as we saw in the Coulomb's law video, for the masses, we always had the case in which masses are positive, of course, which means the force exerted on the probe charge is always an attractive force. For charges, as we know, we don't have this luxury of knowing, of having only one scenario. The charges can be positive or negative. So let's discuss both cases. Let's say uppercase Q is a positive charge, and I want to know the strength and, of course, the direction of the electric field produced by this charge. I want to know, for example, what is the electric field strength and direction at a point situated at distance r from the charge. What I do, I bring a probe charge here that will be positive. The probe charge is always positive. If you are thinking that I am narrowing down the scope of this discussion, remember that I'm trying to discuss and understand the properties of the field produced by uppercase Q, not by lowercase q. So this is just a probe charge. A probe is exactly what the name suggests. It's something that I'm using for probing something else. So I'm okay to call this, to always consider this to be a positive charge. I know that these two charges repel according to Coulomb's law. So the force will be KQQ over R squared. And if I want to find the strength of the electric field at this point, I will divide this force by the point charge. So what I'm left with is KQ over R squared. This is the electric field of the field. It is the electric field of charge uppercase Q at distance little r. And notice how little q is gone. Little q, after all, it was just a probe. When it comes to the direction, if we are looking at this picture again, the force F is in this direction, and I am multiplying it, I'm dividing it by a positive charge. I know operations with vectors, and I know that if I'm multiplying a vector by a positive number, what I get is a vector in the same direction. So vector E will be a vector in this direction. I'm not looking at comparing these two arrows because they represent different physical quantities. This can be shorter, longer, it doesn't matter. These are apples and oranges. What matters is that this vector has the same direction as this force. So I can say, in general, the electric field is equal to the force divided by the charge upon which it acts. Notice here I'm using the little q because this is the probe charge. I'm not talking about uppercase Q. Uppercase Q is the field, is the charge that produces this field. But in order to have a force, I must have a probe charge. Similarly, if charge big Q is negative, I'm bringing my positive probe charge here. Remember, this is always positive. These two charges will attract, and then doing the same thing like we did before, I end up with an electric field being to the left. And this is consistent with this definition. If I have a force, to the left, I divide by something positive, I end up with something that is also to the left. So before we move on to the next page to draw this and to summarize the results, from here I can get the units for the electric field, and the units are clearly Newton divided by Coulomb. And this does not have a special name. So the unit of the electric field is Newton divided by Coulomb. And if I want to summarize this result, I can say, well, if I have a positive charge, the electric field at any point is away from the charge and is given by KQ over R squared. This will actually be true both for positive and for negative charges. So if I am here, the electric field will be, let's say, in this direction. I'm bypassing all the probe charge steps. I know already from the previous page how to get to this vector. If I want the electric field here, it will be on this line and it will look like this. It will be obviously smaller because I'm further away. So this is the electric field at point P, This is, I was going to call it Q, but perhaps it's not a good idea. This is the electric field at point R. You got the idea. If I want the electric field at this point, let's call it S, this would be the electric field at point S, and so on. If, on the other hand, the charge is negative, the same discussion applies, except the electric field will be towards the charge. So if I'm choosing point P here, this will be the electric field at point P. If I'm choosing a point here, this will be the electric field at point R, and so on. To summarize, the electric field for a point charge is given by kq over r squared, and the direction of the electric field is dictated by the sign of the charge that produces it, and the unit is the Newton per Coulomb based on the definition.